move on to the next talk here, and this is Kausik Mukhopadhyay from University of Central Florida. And if I've mispronounced your name, I apologize.
Thank you. Thank you so much. Good afternoon, everyone. It was really wonderful to have this session, especially to start with Christine's talk on lunar dust and plasma, followed by electron beam, dust mitigation from, and then to the lunar, the plasma lunar surface probe. What we are actually trying to look at is over here, because I belong to the material science department with a background in chemistry, what we are going to, our team, which comprises of 3 other faculty from the Material Science and Florida Space Institute, we are going to look from another perspective, and it is a first trial or a very kind of small project that was that came out of interest of dust repellency. And so this is our first attempt to make a durable and supposedly transparent dust repellent coating that can be used for space applications. Next slide, please. So this is my kind of area of expertise from biomaterials, then nanomaterials and catalysis. But specifically, I have a strong focus on surfaces, especially wettability, surface wettability, which can also be looked upon on the other side as surface non-wettability, and coatings, coatings related to anti-fingerprinting, anti-corrosion, ice-phobic, superhydrophobic, omniphobic. But then slowly the omniphobic, usually the terminology is mostly used for liquids, low surface tension and high surface tension. And I slowly directed it towards, let's look at what happens with the solid surfaces, what happens with particulates. And I think that was more drawn towards, like, because of the charged particle that we see from some of the silicas that fly around. So we started with that, and then we wanted to explore a little bit about what happens with the dust. Next slide, please. So to give you the wettability landscape from materials surface perspective, these are the 4 quadrants that I say, and these 4 quadrants are either the water would be, I mean, in a shorter term, either the water can be repelled or the oil can be repelled. Now, with water, we know it has a high surface tension. With oils, by oil, we also mean the organic liquids. It has low surface tension. So with water, it's actually nowadays easy to make the superhydrophobic, which in definition term is having contact angle, anything that is above 150 degrees. But new definitions are, which also should have contact angle hysteresis below 10 degrees, which I will discuss later. And this actually came out from the famous lotus leaf effect. We have seen such leaves, and from lotus leaf, we have seen shark skin and many, many applications. These applications have moved forward with many of the Department of Defense projects related to Air Force, the Army, as well as CBD. But, excuse me. And then on the other perspective, we also have super hydrophilic and super oleophobic, as in the water would be absorbed, but the oil would stay afloat, in a very simpler terms. And these type of surfaces or membranes can be used for oil-water separations. And I think the easiest of them is the one surface that absorbs both water and oil. So we have seen a lot of applications of these wettability landscapes in many of our day-to-day lives as well, including cooking pots and pans. Next slide, please. And this is one, if you don't mind to please press the key, there is a video in there. Yes, thank you. So on this one, what we are, the way to look at it is, so we have developed, this was the first generation of coating, and this is on a fabric. There are two important design characteristics. So this is where we deal with the chemistry. We want to marry the chemistry as well as the engineering aspects of developing a real life coating situation, where two important design characteristics for a composite state on a textured surface are mainly the robustness of the composite interface to pressure perturbations, as well as the aerial functions, which is the air and vapor pockets of the composite surface. Now there are many equations that go along with it, and there are theories. A lot of theories are there, but most importantly, there is a breakthrough pressure versus the robustness factor, which actually plays a critical role to develop such omniphobic surfaces or super omniphobic surfaces. What we do see is what we do know, and there are a lot of papers that have been published and still we are working on, is that optimal super omniphobic surfaces need to simultaneously display high contact angles and high breakthrough pressures with fluids. And this actually comes from the Casey Baxter kind of model, where back in 40s, that theory was developed, where the liquid is supported partially on solid substrate and partially on air. So what we actually did here was this repulsion that we have created, we actually took it to the Casey Baxter level, we created that Casey Baxter substrates that actually repels all types of liquids. Although when we tried with the solid, we were partially successful, and that brought us to like, okay, what are the things that have been developed and where we can develop it more. Next slide, please. And this is where I think we are lucky because we are situated in Orlando. So I took a quick trip to Kennedy Space Center and met with Dr. Carlos, who is a big figure in electrodynamic dust shield, and he was very cooperative enough to show his technology. We spent time discussing about what physical approaches have been taken or currently is on, and what the chemistry, from the chemistry side, what we can look at it. Is there a perspective that we need to take care of, and how we can actually solve this problem? Maybe chemistry and physics can marry together to bring out a new type of coating that can also help in electrodynamic dust shield. So that actually is still in the process, but in the meantime, I mean, we know how the dust shield technology developed from Dr. Carlos and Professor Mazumdar back in the 70s. Next slide, please. And this is kind of he explained like how this the EDS actually works, going through the dielectrophoretic force that is created, and that kind of repels the dust particles. Next slide, please.
5 minutes.
And what we do see, why it is important is, I think a lot of other speakers, many other speakers have already covered this. And I think this is about the spacesuit fabric, the visors, lenses, including the instrument panels, the cameras, everything is important. I mean, and we have seen even on Mars mission, the small helicopter, sometimes it was covered with dust. So, that can actually hamper some kind of transmission as well. Next slide, please. So again, we came back and we looked into it. So what are the design surfaces how we can design surfaces to reduce, solids, and what we call it as a solid fouling. So instead of just liquid fouling, this would be like, the solids are coming and kind of making it a solid fouling system. So how we can repel this dust. And please press on the button. There is an animation. And I think what we are looking at is, please go forward, please. Yes, so what we are looking at is the inorganic scale length, and that's where we are currently focused, because the particle size and all that makes immense interest in that zone. And then we come along, when we looked at the NASA, so we are looking also at the lunar dust aspect ratio, which is exactly not spherical. So we have to actually address that issue as well. Next slide, please. And what we are trying to do here, so before I do, this is the video, and so we have already coated a surface, and this is a kind of coated. So with the coated surface from PDMS brushes that we have created on the surface. So what we are showing here is we did it in-house. We put the coated glass light in there so you can look at the transparency. We took a mud and vermiculite, mixed them together. The vacuum cleaner was used because we wanted to create some velocity, and we wanted to see what happens against the abrasion or against the velocity. And I think we will see very soon how coated versus an uncoated looks like. But what we did here is we actually created excuse me, we actually used polymerization of silane molecules in presence of water. And once they became polymer brushes, these brushes are, what we also did is we wanted to make sure these are durable, because there are many coatings out there which are not durable and they fail in durability. And that's where we actually did we actually created these brushes. But these brushes are also created based on the Casey Baxter model, where they are spaced in a very strategic way with very few nanometers apart, so that there is an air gap, and even if a dust particle come, it's going to sit on top of it. And that's what we are kind of seeing, how coated versus a non-coated, as you can see. So it's the exact same thing. And I think the non-coated, the coated one performed very nicely. One of the important aspects from that Casey Baxter model, or from our model, is to talk about the contact angle hysteresis, which plays a very significant physical significance, because it is directly linked to the lateral adhesion as well as the tilt angle. And this tilt angle is it's the determining factor based on a drop shape model, like when a particle sits on top, how fast it's going to slide. And that's exactly what we are taking care of. Although, as I said, it's kind of a very preliminary data, but we have gotten to a point that we are confident enough that this can move forward with even simulants. Next slide, please.
1 minute. 1 minute.
Thank you. And so what we have also seen is we have coated it on various vacuum collectors, and we can actually coat it on substrate like metals, glass, plastic, composites. We have seen solid repellencies, dust, debris, and regolith. Next slide, please. This can also be put on porous textiles as well as membranes, although we used only 100% cotton. So our next stop would be, gears from astronauts, solid metals, and we can see some of these features, how the low durability, how it works against silica, dust, as well as vermiculite. Next slide, please. In conclusion, we have developed a coating using a chemical approach. It is abrasion resistant as well as transparent. The durability is around minus 20 degrees C. We need to go below that because of the lunar surface. And future work, it depends on, test on some more porous matrices using lunar dust, UV test, dielectric constant, and optical clarity. Next slide, please. I would like to thank the Physical Sciences Lunar Surface Science Workshop, my department and the college, and all my students and postdocs. Thank you so much. If you have any questions, please.
There's one question. Let's see if we can deal with it. Did you control for surface moisture in your dirt sample? Would this still work with a dried sample? And this is from Gordon.
Actually, I had another video, but I knew it's going to be longer. So what we did is we also had a wet dirt, as in a mud. So we mixed it. We took a mud like soil, mixed it with water, and then we actually dropped it down. So it is actually mud resistant as well. And I think one of the biking companies, they are very interested to look into it because, in bikes, they always have this mud issue. So if there is some durable coating that can actually be mud resistant. So one thing leads to other. I never expected that, but very good question. It actually works with moisture.
One thing leads to another, and one talk leads to another too in this session.